Okay, so we just finished talking about probability, both classical and empirical. Today we're going to talk about probability distributions, and these are based primarily on empirical data. So let's get started. And to get started, I just want to give you a few definitions. So the first thing is a random variable. A random variable is just a variable that's associated with each outcome of an experiment. An example of a random variable would be, suppose that we asked people what their favorite car is, and we assigned each car a number. Okay, so if the numbers associated with the cars were 1 through 5, then the random variable would be 1, 2, 3, 4, or 5. If we talked about let's say scores on a test, and we said how many people scored in the 60s, 70s, 80s, or 90s, then we might have 60 as a random variable, 70 as a random variable, 80 and 90. So these are what we mean by the random variables. The random variable is the outcome, okay? So then we have to talk about, well, what kind of random variables do we have? So we have two different types. We've actually talked about both of these because we talked about it when we were talking about collecting data, okay, and the type of data that we have when we look at statistics. So the same thing is true here. This is empirical probability. So we're using statistics. We're using data that we've collected to determine probabilities. So the different types of data that we can collect are discrete. So we have discrete random variables. So a discrete random variable is just like discrete data. This is saying that there are a finite or a countable number of outcomes. Can list all of the different values. If you remember from before, we also talked about continuous data. So we have continuous random variables as well. About the data not being countable. Well, here the outcomes are, we have an uncountable number of outcomes. Fall within some sort of interval, like if you're talking about the speed of a car might be going anywhere from 0 to, let's say, 100 miles per hour. This falls in an interval, but that car could be going at 60.02 miles an hour. So we say that it's uncountable, okay? So it falls within an interval. Line like 0 to 100 would be an example of an interval. but it's not necessarily an integer. In other words, you can't list all of the outcomes. It's not possible. So we could say 0 to 60, we could give an interval, or 0 to 100, but we can't include 60.02 and 60.03 and 60.032. We can't possibly include that. So let's just take some examples. So some examples of discrete. You should take a minute and see if you could think of any on your own. But let's think about the number of phone calls that somebody makes in a given day. This would be discrete, right? Because we can say somebody either makes 1 phone call in a day, or they make 10 phone calls in a day, or 30 phone calls in a day, but you can't make 10.5 phone calls in a day. So the number of phone calls in a day would be an example of a discrete random variable. Sort of work along with me. So we're also going to do examples of continuous random variables. So let's think about another example. The number of days between a guilty verdict and sentencing. Right? If we take the number of days between a guilty verdict and sentencing for somebody who commits a crime, is it discrete or is it continuous? Well, we can actually count the number of days. We could say it's going to be 2 days. It's not, we wouldn't say that it's 2.4 days when we list data like this. So this would be another example of discrete. Another example. Let's say, for example, we talk about the amount of time spent in a jail and infirmary. Well, if we talk about that, are we talking about number of days? We talk about time. So time could be 0 minutes. It could be 250 minutes. It could, if we're talking about days, we might be talking about 3.2 days for something like that. So that might be, because we're talking about amount of time and not specifically a number of days that we can count, amount of time would be continuous. Okay, so amount of time spent in an infirmary. The fact that we're not being specific about the way that we're measuring the time is what makes this more clearly continuous. Another example would be perhaps the speed of a bus on a highway. So again, we're not saying how many miles per hour. We're talking about, well, we're not being specific about how we're measuring that speed. Okay, so if we say miles per hour, it might be 60.2 miles per hour. So the speed of a bus on a highway would also be continuous. Okay, so if we're talking about a specific measure, then it's more likely to be discrete, like number of phone calls. Can we take 2.2 phone calls? Number of days. This one is a little bit more vague because you're sort of saying, can we have 2.2 days? That's not typically how we would measure that if we're trying to figure out the number of days between a guilty verdict and sentencing. But depending on what type of data we're recording, then it might be continuous. It is possible to be continuous. It's possible that it could fit into both categories if we're allowing it to. So depending on how we're measuring it. If we're allowing it to be 2.2 days, then it would be continuous. But if we're saying it's 1, 2, 3, 4 days, then it's not going to be continuous and it's going to be discrete. Okay. The number of hours someone spends making phone calls, that might be another example of continuous, okay? Because you can be on the phone for 2.2 hours. So again, but if we said, okay, well, we're going to say no, you can't, we're only going to measure this as 0, 1, 2, 3, 4, then we would call it discrete. So it kind of depends on how we're allowing it to be measured. So that's why some of these might fit into both. But if we talk about the number of people who could fit on a bus, okay, that's going to be more clearly discrete. Because we can't have 2.5 people. So this one, it can be continuous. If we are allowing answers or outcomes that are now integers. So it depends on how we're measuring that data. Okay, so our probability distributions are only for discrete distributions. They're only discrete probability distributions. And that's because we can't really measure the continuous, we can't write down all of the different outcomes for continuous random variables, okay? So we're only going to be talking about discrete probability distributions. So these probability distributions is for empirical data. So it's based on experiments. Okay. It's, I said empirical data, but I meant empirical probabilities. And if you remember, when we talked about empirical probabilities, we talked about the fact that these are relative frequencies, okay? So when we talk about probability distributions, there are two major requirements. The first is that the probability of each outcome or each random variable has to be between 0 and 1. It ranges from the outcome being impossible, it cannot happen, to being a definite outcome or a certain outcome. And then the second thing is that the sum of all of the probabilities together is going to be 1, because that's going to tell us that one of the outcomes has to occur. So it's possible that we have an outcome that can't occur, but one of the outcomes that we list in there will definitely, at least one of them, okay? So that would mean that the sum of all of the probabilities is 1. So let's write that down. This is how we determine if something is actually a probability distribution. So the first thing is the probability of each variable happening. And remember, we're talking about random variables, which is the same as outcome. So that's why we can use these words almost interchangeably. Of that variable, the probability of the outcome is less than or equal to 1. It's between 0 and 1. Okay, remember the x is the variable. And then the second thing is that the sum of the probabilities is 1. Okay, what we're saying here is at least one outcome must occur. Otherwise, it wouldn't be considered an outcome of the event. So if you remember, I'm going to write this using symbols. If you remember, the symbol for sum is that sigma. So we're saying the sum of the probabilities is equal to 1. Okay, so these are the two things that tell us that something is a probability distribution. So if we want to know if it's a probability distribution, we're going to look at each of the variables. We're going to look at the probabilities, make sure that they're between 0 and 1, and then we're going to take the sum of those probabilities. In other words, we're going to take the probability of the first outcome plus the probability of the second plus the probability of the third and so forth, and make sure that we get 1, okay? And that's telling us that at least one of the outcomes is going to happen, okay? Okay, so let's do an example. So first of all, these are relative frequencies. So a discrete probability distribution it's exactly the same as a relative frequency distribution. So we've done this before. It's just that when we look at a probability distribution, we're saying in the next event, the next time that we do this, let's use the information that we already have to predict what the next answer is going to be. Okay, so let's take an actual example to help us understand this. So let's say, for example, a prison warden is going to administer a personality survey. We'll call it a personality inventory test. And the personality test is there to determine, is that particular inmate passive or are they aggressive, which could be important in terms of what area of the prison you're going to put this inmate in, or even if they belong in a different type of prison. Okay, so the test is measured on a scale of 1 to 5. And we're going to be using this example multiple times in this lecture. And this is discrete random variables because the answers are 1, 2, 3, 4, or 5. Okay, there's no 1.2. 1 would be considered passive, and 5 would be considered aggressive. And just so that, to give you some perspective, a score of 3 would mean that the prisoner doesn't really exhibit either trait. Okay, so I'm going to give you a frequency distribution, and the frequency distribution is going to be based on all of the inmates who are currently in that prison. Okay, so it was administered to every inmate currently in the prison. And then we're going to use this to say, okay, well, what's the probability that if the next prisoner walks in, what's the probable score on this test? A 1, 2, 3, 4, or 5. Okay, so here are the results. So we have our score, which is X. Okay, that's typically how we represent the random variable. And then we have our frequency, which we're going to call F. Okay, so we have these lines are much straighter on my paper, so I apologize that they look pretty crooked here. So we have a 1. We have a 2, a 3, a 4, or a 5. And of the inmates, 24 of them scored a 1. So 24 inmates got a 1. So remember what that means. The frequency distribution has to do with the number of inmates. Okay, these are not probabilities yet. We haven't figured that out. There were 33 inmates who scored a 2, 42 out of 3, 30 out of 4, and 21 that scored a 5. Okay, so now what we're going to do is we're going to create the probability distribution from this frequency distribution. So keep in mind that these are different. This is a frequency distribution here. So probability distribution. Which means that we're just finding the relative frequencies. In order to find the relative frequencies, we're finding what percentage of the population scored a 1, what percentage of the population scored a 2. And we're not really calculating percentage because we're talking about probability, so we're going to leave it as a decimal. So in other words, first we have to find the sum of the frequencies, because we have to know how many inmates there were. So we're going to use that sigma again. So we have the sum of the frequencies, and we just add them together. So we have 24 plus 33 plus 42 plus 30 plus 21. And that tells us that we have 150 inmates in total. Okay. So now we're ready to create the probability distribution. So now we have the score. So we still have the outcome. But this time, instead of the frequency, we're going to have the probability of that score. So we're going to have 1, 2, 3, 4, 5 again. These are our outcomes, or our random variables. You should try and do this on your own. So you might want to consider pausing the video, trying to figure out what the probabilities are, and then start the video again to make sure that you did it correctly. Okay. So for 1, we had 24 out of the 150 who scored a 1. And what this is the equivalent to is 0.16. So that's the probability that the next inmate who comes into that prison is going to score a 1. Okay. For the 2, well, 33 out of the 150 scored a 2, and that's a probability of 0.22. 42 out of the 150 scored a 3, and that's a probability of 0.28. This is a 42. For a 4, 30 out of the 150 scored a 4, and that's a probability of 0.20. And for a 5, 21 out of 150 scored a 5. So that says 0.14 is the probability that the next person scored a 5. So let's write this. This is a probability distribution here. And this number here tells us this is the probability the next inmate who enters the prison there's a 4 or a 3. Okay, so let's verify that this is a probability distribution. So I'm going to do this on the next page because we're kind of out of room here, but sorry. So we're going to verify. And essentially when we say that we're verifying that this is actually a probability distribution. And we already know it is, but we just want to make sure that we did everything correctly. Okay, so we're going to check for our 2 requirements. So the first thing is each probability, meaning each P of X, is between 0 and 1. And this we could sort of see as we go through it, right? 0.16, 0.22, 0.28, 0.20, 0.14. These are all numbers between 0 and 1. So that part we can verify as we go along. The second thing we actually have to calculate. So we want to make sure that the sum of the probabilities equals 1. So we're going to add the 0.16 plus 0.22 plus 0.28 plus 0.20 plus 0.14, and that is equal to 1. So this verifies that we have a probability distribution. Okay. Now let's create a probability histogram. So this is just like a relative frequency histogram. We're calling it a probability histogram because we're using it to predict the future. We're not using it to show what happened in the past, and that's why we say probability. A relative frequency histogram is simply to show, okay, well, 14% of the people in the prison scored a 5, whereas this is just a slightly different perspective, and it's saying, okay, there's a 0.14 probability that the next person who walks into the prison scores a 5. Okay, so if we do this, these are our scores, these are our x's. And these are our probabilities. So we'll go up by 0.05 here. That's reasonable because if we look at our probabilities, the highest that we have is 0.28. So it makes sense to go up by 0.05. We could stop at 0.30. And then here we're going to put in a 1, a 2, a 3, a 4, and a 5. And what we're doing is that 1 is kind of in the middle of our bar. Okay, so our first bar goes up to 0.16. So notice we're not centering it around 0, okay, because we never actually hit 0. So this is 0.16, then we have a 0.22. We have 0.28. We have 0.20. probability distribution. And you'll see some probability distributions. We've seen this in the frequency histograms where it actually puts the probability above the bar just so that you can see it. One of the things that I'm just going to mention now because it's going to become more important later is when we construct the probability histogram. The width of each bar is 1, and the height is the P of X, right? The height of this bar is 0.16. It's the probability of X. So I'm going to actually add that in over here. So the area of each bar is just 1 times P of X, or P of X. Again, this is just to mention it now. It's going to become more important later, so don't worry about it too much at this moment. You're just saying, okay, well, this has a width of 1 and a height of P of X. So when we do the area of the bar, it's width times height, okay? And that is just going to be P of X, okay? The other thing that we can see from here is that this is approximately symmetrical, right? So you've been looking at curves a lot. If you've been watching the news or reading the newspaper, you've been looking at a tremendous number of curves over the last few weeks even. And you've been getting a lot of different types of curves. Most of them look pretty symmetrical. So this is another example of a symmetrical curve, right? It peaks and then it comes back down at about the same rate that it went up. So we would say this distribution is approximately symmetrical versus skewed right or skewed left. Okay, let's do another one. Let's say that this time we're looking at the number of overtime hours used by employees. So I'm going to give you the frequency distribution, okay? So we have the overtime hours. I'm going to do this horizontally instead of vertically. And we're going to have the number of employees that take that number of overtime hours. So depending upon how you measure this, right, this could be discrete or continuous. However, most of the time when employees get paid for taking overtime hours, they get paid by the hour, sometimes by the 15 minutes, but we're going to do by the hour. They don't, if they take 1 hour and 3 minutes, they're not getting paid for 1 hour and 3 minutes. They're getting paid for an hour. So because we measure this by the hour, this would be discrete instead of continuous. Okay, so this is an example of the way in which we measure something can change the type of random variable. So we say, okay, well, we have employees who don't take any extra hours. 1, 2, 3, 4, 5, and the maximum number of overtime hours that an employee can take is 6. Okay, so the frequency distribution says 6 people, 6 employees take no overtime. 12 take 1 extra hour. 29 take 2 hours. 57 take 3. 42 take 4. 30 take 5. And 16 take 6. Okay, so the first thing that we have to do is we have to find the sum of the frequencies, right? Because in order to determine the probabilities, we need to find the sum of the frequencies. So all we have to do is add the frequency for each outcome. And if you haven't already, you should consider pausing the video here, constructing the probability distribution, verifying it, even go ahead and create a probability histogram and do that on your own, and then come back and start the video again. Okay. So if we add all of these together, we find out that we've surveyed 192 employees. So the probability distribution tells us when we hire somebody new, okay, so a 193rd person, what is the probability that they don't take any overtime, or they take 1 overtime hour, 2 overtime hours, and so forth? Okay, different than the relative frequency, because relative frequency tells us, okay, well, a certain percentage of employees took this amount of overtime. So we're not doing any prediction with the relative frequency, but it is giving us the exact same information. Okay, so we're going to construct a new, so this is the frequency histogram, frequency distribution. Now we're going to construct the probability distribution. So our probability distribution is still overtime hours. It's still our random variable, which we'll call it X. And then our P of X. So the probability that our next person takes no overtime is 6 out of 102, meaning a probability of just 0.03. For 1 hour, it's 12 over 192. So if you calculate that, that's just 0.06, very small probability. For 2, it's 29 over 192. So this is 0.15. For 3 overtime hours, it's 57 over 192. That's 0.30. For 4 hours, it's 42 over 192. That's a probability of 0.22. Five hours is 30 over 192, which is 0.16. And finally, 6 hours is 16 over 192, which is 0.08. I'm gonna write that, it kind of went off the page, so I'm gonna write that again. Oops. I'm going to write it over here, 0.08. It's not totally clear. I'll write it down here. Maybe it's a little bit clearer. Okay, so it's equal to 0.08. So again, we're just going to verify. So you don't really have to verify the first one because you kind of know it. Each probability is between 0 and 1. And I'm going to write it a little bit differently right here. I'm going to say 0 is less than or equal to p of x, which is less than or equal to 1. Okay, just as a shorthand. And we're going to take 0.03 plus 0.06 plus 0.15 plus 0.30 plus 0.22 plus 0.16 plus 0.08. And this is equal to 1. So the sum of the probabilities is 1. So this is a probability distribution. We're not going to do a probability histogram, but you can see that the probabilities are higher, a little bit higher, more towards the right, but they still go up, they reach a peak, and then they come down. So if we do the probability distribution, the probability histogram, it is going to look pretty symmetrical, but it's probably going to look, if it's skewed at all, it's going to be skewed to the left, where on the left you have more of a tail than on the right. Okay. Okay, so let's just take some examples where we are verifying that something is a probability distribution. Remember, we verify in two ways. We look at the probability of each outcome. And those all have to be between 0 and 1. The first thing. Second thing is look at the sum of the probabilities. So we've been doing this already. And we know that the sum of the probabilities has to equal 1. If it doesn't, it's not a probability distribution. So let's just take one example. So let's say that we have a probability distribution, or what seems to be a probability distribution, where our random variables are 1, 2, 3, and 4. And the probability of a 1 is 0.09. Probability of a 2 is 0.36. Probability of a 3 is 0.49. And the probability of a 4 is 0.1. Okay? So this satisfies A. All of our probabilities are between 0 and 1. Now let's look at B, right? 0.09 is between 0 and 1. So it's 0.36, 0.4, 0.1. These aren't negative. Okay, and they're not greater than 1. Okay. So now we're going to add the probabilities. So we get 0.09 plus 0.36 plus 0.49 plus 0.1. And if we calculate this, we actually get 1.07. This is not equal to 1. Okay? So this is not a probability distribution. It looks like a probability distribution, but it's not. So that's just what you would do if you're given a probability distribution and it's saying, okay, is it actually a probability distribution? Okay. Okay, so the last section of this is really the mean, the standard deviation, and the variance, okay? So the mean, I'm gonna just put a dashed line here because we're sort of touching upon something that's related, but it's in sort of another perspective of all of this. So the mean of a discrete random variable so we use this mu, and this is equal to x times p of x. Okay. Okay, I'm running out of ink, so I'm just gonna... Okay. So we have the mean is equal to the sum of x times p of x. So here's what that means. That means that what you're going to do is you're going to take the random outcome, the random variable, you're going to multiply by the probability, and then you're going to do that for each outcome, and then you're going to take the sum of them. Okay, so let's use the example of the passive aggressive, okay? This is what we did at the beginning. We called it a personality inventory test. So I'm just going to rewrite the probability distribution here, just so that you have it again on this page and you don't have to go back to the previous page. So we had the score, which was x, and then we had the probability of x. I'm going to do it horizontally. So we had a score of 1, had a probability of 0.16. A score of 2 had a probability of 0.22. The score of 3 had a probability of 0.28. 4 had a probability of 0.20. 5 had a probability of 0.14. Okay, so here's what this means. We take the 1, we multiply it by 0.16. We take the 2 and multiply it by 0.22. The 3, we multiply it by 0.28. The 4, multiply it by 0.20. And the 5, and we multiply it by 0.14. Okay, and what we get here is 2.94. So a couple of things. What are we actually doing here? Okay, so what we're actually doing is we're saying this 1 occurred 24 times. So I'm going to rewrite here actually the frequency distribution too, because I think that that'll help. So the 1 occurred 24 times. The 2 occurred 33 times. 3 occurred 42 times. 4 occurred 30 times. And 5 occurred 21 times. So what's actually happening here is we're finding the mean, but we're using the frequencies to help us. So this is just a much shorter way of doing it. We're doing 1 plus 1 plus 1 plus 1 24 times. There are 24 of these. Then we're adding to that 2 plus 2, 33 times. And then 3 plus 3, 42 times. And then 4 plus 4. This dot 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 just means that we just have more 4s. This is 30 times. And then plus 5, plus 5, and so forth. And this is happening 21 times. And then we're taking this whole thing, and in total we have 150 of these. So we're dividing this whole thing by 150. So we're taking the mean of all of our answers. Okay, so this is actually a really nice short way of doing it. We're saying we're taking 1, and 1 occurs 24 out of 150. Then we have 33, and that's occurring 33 out of 150 times. So we're saving ourselves a lot of trouble by doing it this way. But what we're really doing is we're taking the mean of all of the answers, okay? And I want you to notice that this 2.94 is not necessarily an outcome. Right? It falls within a range of our outcomes. So in other words, it's not going to be 6. It's got to be between this 1 and 5. Okay, that's the range of our outcomes. But that's what we're doing here when we find the mean. So our answer few things to know about this answer. The first thing is our answer will always be in the range of outcomes. In other words, in this case, it'll be between 1 and 5. In the other example that we did with overtime hours, we were saying it would be between 0 and 6 because that was the range of our outcomes. average, we call it a theoretical average. Another thing that we call it is the expected value. In other words, if we do this experiment thousands of times, okay, we would expect the mean of the distribution to be very close to just the mean of the outcomes, okay? So expected value would mean essentially, what do we expect to happen for the next person? And we kind of know that it's going to be close to, let's go back a couple of pages. Here we kind of know it's going to be very close to 3, because look at the probabilities. The probabilities are centered around 3. So it makes sense that our expected value is going to be really close to 3, okay? Let's go back here. If we were to do this experiment thousands of times, so instead of asking just 150 people, we asked 1,000 people. The mean of the probability distribution which is the sum of the x times p to the x. Is going to be close to the mean of the outcomes. In other words, in symbols, what we're saying is the sum of x times p of x times the probability of x is going to be very close to the sum of x over n, where we're saying that n is equal to the number of outcomes. So if we were to take this case again of the 1 through 5, we're saying 2.94 would be close, okay, to the average of the outcomes, which is 1 plus 2 plus 3 plus 4 plus 5 over 5. And if we find that, we get 15, and if we divide by 5, we get 3. So 2.94 is approximately equal to 3. And as we increase the number of experiments, so in this case, the number of inmates who we give the test to, the sum of x, p of x, will get closer and closer to 3. So right now it's 2.94, but it's going to get even closer let's do one more. Let's find the mean of the overtime hours. So let's take the probability distribution. I'm going to rewrite it here. X, which was overtime hours. And P of X. Again, this is on one of the previous pages, but I'm just putting it here too. So 0 hours was 0.03, 1 hour was 0.06, 2 hours was 0.15, 3 hours was 0.30, 4 hours was 0.22, 5 hours was 0.16, and 6 hours was 0.08. So at this point, you may want to pause the tape and try and find the mean yourself, okay? And then you can check it against what we find here. So the first outcome was 0, and the probability of that outcome was 0.03. So in other words, that's like adding 0. It's adding 0 6 times because the frequency was 6, okay? So it does matter how many times you're adding 0, even though it doesn't make a difference in the sum. Remember, you're dividing by a larger number, right? We're still dividing by 192. So those 6 zeros actually do make a difference in the average. So then we have 1 times 0.06 plus 2, the probability of 2 is 0.15, plus 3, probability of 3 is 0.30, probability of 4 is 0.22, probability of 5 is 0.16, and the probability of 6 is 0.08. And if we do this, we get 3.42. And you can see it's still relatively in the center, and that's because this is approximately symmetrical, okay? One note is that if one of the outcomes is negative, then our expected value or our mean could be negative, okay? So if we were talking about the amount of money that we lose, okay, and we were talking about loss as -1, we lose $1, so we count it as -1, and all of our outcomes are negative, well, then our mean is going to be negative, okay? Our expected value is going to be negative because our expected value is somewhere within the range of the outcomes. So I just want to write that down so that you know that it's okay to get an expected value that's negative if you have outcomes that are negative. This isn't the case here. We don't have any negative outcomes, so you are not going to have an expected value that's negative in a case like this, okay? At least one of the outcomes has to be negative in order for that to happen. Okay, now the last thing is just looking at expected value and variance. Not expected value, variance and standard deviation. And this is very similar to variance and standard deviation that we've done before. Okay, so again, this is the spread of our data. Okay, how are we going to just wanted to make sure it was still taping. How are we going to how varied is our data? Okay, so again, we're going to look at the personality test for prisoners, and we're going to calculate the standard deviation and the variance based on that. So variance, this is just like what we've done before. Okay, it's the average distance from the mean, right? So we take the x minus mu, because that's the difference from the mean. We square it so that we don't get negative numbers, and we multiply by the probability. Okay, so we're still taking average distance from the mean here. This is variance. So if you remember standard deviation, we're essentially undoing the square. So it's just, this is a sigma. So it's going to be the square root of this. It's the square root of sigma squared. So it's going to be the square root. So again, we have the distance from the mean for each value. And then we're taking an average, right? So the average here is multiplying by p of x. Instead of dividing by n, we multiply by p of x. So I'm just going to set up a chart here and just follow along with the chart, okay? So we have our x. We're setting up the chart based upon what we see in our formula. So first we need to know our axes. So our axes here are 1, 2, 3, 4, and 5. So our p of x, we need to know is, actually we don't have to put p of x next. I'll do it in the order that we see it in the formula above. Okay, so let's put mu next, just so that you have it in your chart. So your mu is 2.94 for each of these. Okay, just like what we did. So a little note here that mu is the sum of x times p of x. So we already calculated this on the last page. Okay, so then we're going to do x minus mu. So we get negative 1.94. We're just subtracting here. Negative 1.94, negative 0.94, 0.06, 1.06, 2.06. So we're subtracting the first two columns. We're doing 1 minus 2.94. That's what gives us the negative 1.94. 2 minus 2.94. That gives us the negative 0.94. 3 minus 2.94 gives us 0.06. So we're doing that for every one of our x values, the first column minus the second column. Now if we add this together, we have the same problem that we had before when we were finding the standard deviation of data. When we added it together, we got 0. So we have to square it to prevent that from happening. So we have x minus mu squared. We're not going to round so much here. We're just going to do 3.7636. This is going to keep it as accurate as possible. 0.8836, 0.0036, 1.1236, and 4.2436. Okay, so we're taking this column and we're squaring it. So now we have to do a multiplication, right? So we need to find P of X. So P of X we already know. We're taking that from our probability distribution. So the probability of getting a 1 was 0.16. This comes directly from the probability distribution. Then we have 0.22, 0.28 for 3, 0.20 for 4, and 0.14 for 5. And remember, the sum of our P of X column is 1. So our last column is just going to be this one times this one, okay? X minus mu squared times P of X. So we're going to multiply these last two columns together. Okay, so I'll write it out for this column, but I won't do it for all of them. We're doing 3.7636 times 0.16. And we get 0.602176. Then we get this one when we multiply, we get 0.194392. Again, we're multiplying the last two columns. We get 0.001008, 0.224702, and then I'll write it again here. We're doing 4.2436 times 0.14. So that gives us 0.602176. Sorry, that's not what we get. I wrote that wrong. I was looking up above instead of at what was actually calculated. 4.2436 times 0.14 is 0.594104. That's what we get. Okay. Okay, so now we're going to find our sigma squared. So our sigma squared is the sum of that last column. We're just going to add it all together. So I'll write it down here. It's 0.602176 plus 0.194392. Then we're adding the next one, 0.00. 108, sorry, 1008. Plus 0.224702. And finally, plus 0.59414. And what we get as the standard, as the variance is 1.6164. This is our variance. And our standard deviation is just the square root of this. And the square root of 1.6164 is 1.3. This is variance. This is standard deviation. And again, it just tells us what the spread of the data is. Okay, where the average distance from the mean is 1.3. Okay, that's what it's telling us. And that's it for this one. Okay. So this is everything that you need to know about probability distributions. Again, it's so similar to all of the things that we have already done.